So now we have Tariq and Alfredo coming to talk here. So a bit longer interaction because we have two speakers. So Tariq from CODASIP is one of the architects turning CHERI into a deployable industry standard. As chief architect at CODASIP and a long-time RISC-V standard contributor, he spent decades in Silicon and the last 5 years driving CHERI into the mainstream. Today, he'll ground CHERI progress where it counts most: real standards, real hardware, and real adoption. And Alfredo Mazzinghi, University of Cambridge. Alfredo works on the practical evolution of CHERI at the systems and architecture level. At the University of Cambridge, his research focuses on strengthening memory safety mechanisms and making CHERI more robust and deployable in real systems. So we'll hear about you.
Okay. Hi, everyone. So we're here to give a brief overview of the MMU-based revocation scheme that we have in the standard. So, brief agenda. What is revocation? Some very brief details of revocation algorithms. This is a big, complex topic, so we're really not going to go into details during this. It's really just an overview. And then Alfredo will take over and talk about implementing the algorithms on a CHERI-based system with an MMU. So what is revocation in this context? Revocation is the act of locating and invalidating stale or dangling pointers. So what we're looking at is dynamic memory allocation, where memory is allocated using malloc. Sometime later, it is freed via a call to free. When you call free, there may be pointers left to that memory region. And what we need to do is find those pointers and remove them to prevent use after free and use after reallocate vulnerabilities. So use after free, we say, is where the use of the pointer is before the memory has been reallocated, and use after reallocate is after the memory has been reallocated, somebody still has a pointer to it. CVEs list both types as use after free, and so they don't actually distinguish. But I have an example there of a CVE 2026-2441, so one from this year, of a real example of one of these. And they're really, really common. So next slide shows that use after free, which is including use after reallocate, is about half of the memory safety vulnerabilities in Chromium. Pardon me. So this is taken directly from chromium.org. and gets updated regularly. But we can see that the spatial safety is the red part and the temporal safety is the blue part. So actually in this case, it's slightly more than the spatial safety. So what can we do about this? Well, the big advantage with CHERI is that we actually know what a pointer is, because if it's a valid capability, it's a pointer, most likely. So it means we can accurately identify pointers and invalidate them, and there's no non-determinism when we're doing that. So this gives a big advantage over non-CHERI architectures, where you may have to use heuristics to identify pointers, and you're basically guessing. And then how do you invalidate a pointer on a conventional architecture when you can just access memory through a random number and see what happens, which is what CHERI guards against. So in a system where you can't just make up pointers, we can actually find them and invalidate them. So we've had at least 3 papers from Cambridge University and based on research from Microsoft Research as well on algorithms used here. So the first one, CHERIVOC, introduced the stop and sweep algorithm, where after calling free and maybe batching up multiple calls to free, you stop the application, you sweep all of virtual memory to find dangling pointers, and then you restart the application. So completely effective, low performance, because you're stopping the application for a long time. And then Cornucopia and Cornucopia Reloaded both introduced ways of improving the performance. So Cornucopia involved the concept of background sweeping and having epochs, which I won't go into the details of. Cornucopia Reloaded gives sort of more concurrent operation and turns most of the operation into a background thread which runs under the CHERIBSD or Linux kernels. So the cornucopia reloader scheme is implemented on Morello and runs on CHERI-BSD and is currently being ported to CHERI-RISC-V. So for the MMU, what do we need to do? So for CHERI-RISC-V, we started off allocating 2 page table entry bits, and then last year we moved to 3 table entry bits, and then this year we moved to 4. And having 4, we completely mirror all the states that Morello has. So we have a load barrier, which lets us prevent loads from pages which may need to be scanned for capabilities before the capability is actually loaded, and which uses 2 bits. And we have capability dirty tracking, which tracks which virtual memory pages have had capabilities stored to them. And I shall now hand over.
Press down. Down, okay, cool. Hello. So I'm going to give a very quick overview of what cornucopia reloaded implements for Morello. It's fairly high level, so I'll keep to the general algorithm essentially and not focus on too much on details. So in this implementation, the revocation is really a shared responsibility between user and kernel space. And so you have a revocation state for each address space because capabilities exist in an address space. And your memory allocators must ensure a few things. They manage a quarantine that keeps memory from being immediately reused. It maintains a shadow bitmap where it marks which parts of the memory are freed and should be revoked. And it's in charge of recycling the memory from the quarantine into the free list of the allocator once the revocation sweep is done. And the kernel space exposes a revocation API because the revoker thread, the background revoking scan, is done by the kernel. And it's triggered by user space through a system call interface. And so the kernel provides the actual backing storage for the shadow bitmap, which is provided to the allocators for them to paint them, the shadow bitmap. It maintains the epoch counter that tells you in which revocation epochs your user space is, and so it gives you a timing information to move between one epoch and the next to mark, to detect when capabilities can be reused. So at a very high level, we can identify a few basic blocks, building blocks of this implementation. So at the top, you have your application code that just does its normal free and mallocs and frees. In your allocators, you have your usual free lists, and now we introduce a quarantine that keeps memory from going directly into the free list, but instead waits for some time before it can be reused, and thus breaking the use after reallocation. The allocator decides when to move memory from the quarantine to the free list, conceptually, using this epoch counter that is maintained by the kernel and read by userland to determine essentially when the memory has been revoked. And there is a shared shadow bitmap between user and kernel space, and it's maintained for each mapping that you have in your address space. And the background revoker is fully in the kernel. And you have this CHERI-RISC-V system call interface that is used to trigger revocation and drive the kernel from userland. So at a very high level, these operates in phases. You start from, I try to be fairly abstract here. You have an epoch counter, which I mark here as abstract epoch. Let's start with E0. And these then corresponds to an architectural value in one of your status registers. In RISC-V is UCRG. You have your program that does its own work, and at some point it decides, oh, I should probably revoke some memory. And so it triggers the revocation through CHERI-RISC-V, and you split this into the revocation, actual revocation is split between a barrier phase and a synchronous revocation pass. And the synchronous pass actually runs in parallel with your program. So the barrier phase instead is synchronous, and it's kept as short as possible because that's when you're actually stopping the threads of your program, of your process, and sweeping and ensuring that the register file is clean. What does it mean? It means that the end of the barrier phase, you have an invariant, and the idea is that you cannot have a revoked capability in your register file at the end of the barrier phase. So if you have a capability that has been marked as revoked in epoch 0, by the end of the barrier phase, you can't have it in the register file anymore, and you can never load one. And during the asynchronous revocation pass, you have this load side barrier that is implemented through PTE bits, fundamentally, where capability loads are interposed, essentially. Whenever you do a capability load from a piece of memory that the revoker hasn't observed, you go and inspect the capabilities to make sure they don't end up in the register file. So the barrier phase actually does a few things. At a high level, apart from bumping the epoch and managing the epoch counter, it actually sweeps the register file and doing the synchronous phase where you don't have any other threads running. And then it needs to go and look for places where you may have stashed capabilities in the kernel. And this is, to give an example, AIO system calls, they stash user pointers in the kernel for extended period of times and can be there across revocation sweep. So you have to go and revoke them. The asynchronous sweep instead is split in these two parts because it's concurrent between user and kernel space. On the kernel side is well, relatively simple. At the high level, you have this revoker thread that scans memory. I use the green to mark pages that have already been observed, and the revoker goes down, essentially, scanning each page. For every page that it hasn't observed in the old generation, it will load every capability aligned piece of memory, check whether it contains a capability. If it does, it will check in the shadow bitmap whether it has been painted by the user space allocator as being freed. And if so, it will invalidate it and store it back. At the same time, your program tries to do actual useful work. And so it will normally load capabilities from memory. And when it loads capabilities from pages that have already been observed by the revoker, everything is fine. You're sure that you don't have unrevoked dangling pointers in there, and so you can easily access them. But if the revoker hasn't observed the page, the PTE bits will mark it as being in the older epoch, in the previous epoch, and so you will trap, and the kernel sweeps that page on demand, make sure that there are no revoked capabilities in there, it invalidates them, and then lets the program run again with its own work. So, as you can imagine, sweeping memory is not cheap. DRAM traffic is not cheap. So there's been a lot of work in trying to make these performant and have a good acceptable performance characteristic, right? And so one thing that we try to do very hard is to avoid scanning pages without a good reason. And we do this by detecting, well, you can both mark pages as never being able to store pointers, which is the case, for instance, for file mappings. There is no reason why your file mappings should hold pointers. So you can obviously skip them. But there are sometimes cases in which you have a page that can hold capabilities, but just happens not to have any during a particular scan. And so what you end up doing, you have a lot of machinery that tries to detect this and skip scanning these pages that you're sure cannot have any capabilities in them. There are various sources of complexity here, just to give you a general overview. Alias mappings are particularly problematic to detect the fact that you don't have any capabilities in there, because you can imagine racing and storing capabilities through one of the alias mappings while you're scanning the other one. Super pages and large pages are also a source of problems in a sense, because as you take a fault due to an access in one of these huge pages, you have to scan the whole page, and so if you have to, and so it's a problem for latency, because if you're interposing a load from a 4K page, you just scan the 4K page. If it's a 2 megabytes page, that's going to take longer, and so you delay your program for a longer amount of time. And then there is a lot of work in cornucopia to minimize TLB invalidations, because every time you update the PTE bits during the revocation scan, ideally you would have to do TLB invalidations to shut down specific pages in the TLB, and we try very hard not to do that. And so finally, the state of support, what you get right now. Current QEMU implements RV64Y on the older 093 spec. We have patches for the new updated 4-bit implementation, but we are holding on. And of course, the MMU-based revocation work has been mostly focused on RISC-V 64, but there are different approaches possible, and CHERI definitely shows that other approaches possible in 32-bit architectures. Thank you.
Maybe, yeah, maybe one question, because we are running a bit late. Oh, that was very clear then.
I confused everybody. Right?
Everyone is like, what? Okay, one.
Yeah.
It's more of an observation and a question. It looks like you basically created an ACID database with a vacuum thread.
Sorry?
It's more of an observation and a question, but it looks like you basically created an ACID database with a vacuum thread to clean things up. Is it, in a layman's terms?
Yeah, interesting. Yeah, it's an interesting comparison, actually. I never thought about it in that way. But yeah. Yeah, we generally think about it as a garbage collection.
Yeah. Sorry, I'm an ex-database engineer. So.
So thank you again. Thanks to both of you.